We share.
Tutorial questions and answers.
It is all about understanding facts and sharing with others.
Learning continues. We are learning to know, understand, and share with others.
Please subscribe to our channel if you like our videos.
Welcome. In this video, we are going to deliberate on 3 different tutorial questions. So the first question now is this. Using at least one example of a linear ordinary differential equation, explain what you understand by a singular point, regular singular point, and irregular singular point. Now, look at the answer to this question. Now, in the question, you have to use one example of linear ordinary differential equation. So let's look at equation 1 now. Look at equation 1. You see that equation 1 is actually a linear differential equation. So you can see it's a linear differential equation. So look at it. Px here is a function, qx is a function, and then rs is a function. F of x is a what? Is a function. Now look at it now. In this case, p of x should not be 0. So if you divide both sides by p of x, you have equation 2. Look at it. You only need to divide both sides of equation 1 by p of x. So you have this one. Now definition 1. Px0 is 0. We call x0 a singular point of equation 1. Look at why I focus on px0. The denominator here is actually px. So if there is a particular x0 and you put inside the p of x here that you have 0, then it means that x0 is a singular point of this equation 1 or equation 2. Now let's look at definition 2 now. The singular points mentioned above, this is the singular point, which is x0. We want to know if it's a regular singular point or irregular singular point. So what do we need? Look at this definition now. X minus x0, then multiply by this, which is what we have here, and then x minus x0, the square of it, multiply by this one. If they are analytic at x equals to 0, then we can say that it's actually a regular singular point. If this is true, then we can say it's a regular singular point. But otherwise, we say that it's an irregular singular point. Now, look at what I put down here now. I said, if equation 1 has a regular singular point at x0, there may be no power series solution about x0. Remember, Dr. Dowd have explained to you power series, okay? So what we are trying to say now is that if equation 1 has no regular singular point, we have ordinary and we have regular singular point. If you don't remember ordinary, go and check your lecture notes, page 4. We see where I explain ordinary point. Ordinary point is very simple, you see there. But here we're talking about singular points. We're talking about regular singular, we're talking about irregular singular point. So what we are saying is that if this is true, and x0 is the singular point, if this and this they are analytic, then it means that the singular point is actually regular. And that is why we can use Frobenius series solution. Look at that Frobenius series solution. You notice that I didn't explain it like this. What it's actually saying is that y of x is a solution, summation from r to infinity ar, the x minus x, this x0 is the singular point, then k plus r. Most times x0 equals to 0 is always singular point. That is why most times you don't write this minus x0, because if x0 is 0, then you see now that it's more or less like the way we've been using it before. Now let's consider example 1. Example 1, look at this problem on the board here. Okay, look at this problem. Can you see there now? This is second order linear ordinary differential equation. Divide both sides by p of x. Here now, this is my p of x. Can you see that now? So by the time you divide, but by the time you divide both sides by p of x, you now have y prime prime. Then you have everything divided by this 5 divided by p of x. Now let's go again. You notice that x squared minus 4 squared is the same thing as x minus 2 squared, x plus 2 squared. So you change the denominator of p of x. This p of x, you change it. So by the time you change it, now look at this it's very simple. From here you can see now that when you set x equals to plus 2, this one here will give you 0. This one will give 0. Then you have 3 over 0, that will be 0. This one too will give you 0. Then in that case, we can say that plus 2 is a singular point. What about minus 2 again? You see that minus 2 is also a singular point. So for this particular differential equation, we have 2 singular points. Now, next stage is now for us to classify what type of singular point are we talking about. Is it regular singular point or irregular singular point? Now, let's take a look at that expression. Look at that expression. Okay. And we said that if this and this one, if they're analytic as x equals to x0, then it means that it's actually the singular point is regular. So Look at this now. This is for the case of plus 2. You know, we have two singular points for the case of plus 2. So x minus x naught. Then this is my q of x. This is my p of x. P of x is the denominator. So what's the next thing? This one here, we actually cancel this one here. Can you see that? Let me press Ctrl Z. Okay. This expression, let me highlight it red. We actually take care of this expression. So what remains is 3 over x plus 2 squared. So we have this. Now look at the second one again. Look at the second one. But do you notice something? If you should put plus 2 here, plus 2 is 4. 4 squared is 16. So definitely this one is 3 over 16. If you put 2 here, 2 plus 2 is 4. 4 squared is 16. This is actually 5 over 16. So you see that this one is what? Is a finite. What we have here is a finite. What we have here is what? Is a finite. Let me bold it. What we have here is a finite. What we have here is also what? A finite. So we can answer that both of them, they are what? Analytic as x equals to x2. This is true because this expression and this expression, they are finite when x equals to what? Plus 2. So hence we can say that x plus 2 is a what? Is a regular singular point. Let's take a look at the second one again. When x is minus 2, we have x minus x naught. That's x minus x naught. You know, my x naught is what? Is minus 2. So you have this, and look at this one. This one will give you 3 over x minus 2, x plus 2, because x plus 2 here, we take care of one of this. Now, what about the second one again? X minus x naught squared. Don't forget, where do you get this rx, px? They are the coefficients. Look at it, rx, they are the coefficient of y. Okay, so let's continue with this solution. So you have x minus x naught, that's x minus 2. Then this one. Now, look at this one now. This expression here is not analytic. Because by the time you put minus 2 in this case, let me put here. By the time you put minus 2 here, this one will give you 0. 3 over 0 is what? Is infinite. And if it is infinite, it means that it is not analytic, because analytic means that it must be finite. But look at the other one here. By the time you put minus 2 here, minus 2 minus will give you minus 4. Minus 4 squared will give you 16. That's 5 over 16. And 5 over 16 is what? It's finite. So this one here, this expression here is analytic, while this one here is not analytic. So what does that mean? It means that x minus 2 is a regular singular point. So that is the end of this tutorial question. Now let me read again. The tutorial question says that using at least one linear ordinary differential equation, explain what to understand by singular point, regular singular point, and irregular singular point. So that is the end of our tutorial question 1. So let's go to tutorial question 2. Look at tutorial question 2. Now, this tutorial question 2 says that using Frobenious method, you should align the nature of solutions of the indicial equations. Okay, nature of solutions. You know that indicial solution, indicial equation will give us quadratic, isn't it? And by the time we solve this quadratic equation, we are going to have 2 points, 2 values. Now, there are 3 things involved. Number 1, if the root of the indicial solution, if they are not equal, and the difference between them is not an integer. Let me give you an example. If k1 is 0 and k2 is 1 over 2, you know the difference between 0 minus 1 over 2 is what? Is half. Okay, so if that is the case, then the 2 independent solutions, they are now what? We have our y1, then we have r0 to infinity, ar, s, kr plus r. See, this kr, you put it down here for the first one. For the second one, you have k2. Now let's go to the second case. Second case is this. If k1 is not equal to k2, but k1 minus k2 is an integer. Let me give you an example. Now, let's say you are solving a particular Bessel equation or any differential equation that has to do with special functions, and the roots of the indicial solution, they are not equal. Let's say, for instance, the first one is 1 and the second one is 2. Remember that 1, or let's say 2 and 1, the difference is what? Is 1, and 1 is an integer. In that case, there's something you must do. What are you going to do? The first solution will be y1 summation r to 0 r s k r s raised to power k1 plus r. That is the first solution. Let me bold it. Then what about the second solution? The second solution will now be k multiplied by y1. That is what you obtain here. Then ln of x. Then plus summation r0. Then ar s k2 plus r. That is how to obtain for the second one. And here, this k here is actually constant. By the time it can be 0. In some problems, it can be 0. Now let's talk about the third category. The third category is when k1 is k2. Let me give you this example. A typical example of this third category is when we are solving Bessel differential equation of order 0. You notice that we only have one solution. And I said that is not all. That solution we have is actually a z function of order 0, and that is for this case now. But what this one is saying is that in this case, we have two solutions. And the first solution is this. The second one is y1 multiplied by ln x, then plus summation r0 to infinity ar sk2 plus what? Plus r. So take note of this. These are the three categories of what we refer to as the solution of the indicial equation. Okay, tutorial question 3. Tutorial question 3 says that we are to use the method of Frobenius to obtain the solution of the problem on the board, which is equation 5. Now look at this problem now. As you can see clearly from here, we cannot proceed with this, and this is actually Bessel Differential Equation. So before we proceed, before we even conclude, maybe we should use Frobenious method of solution. Remember what I've said in class, that you need to conclude, you need to tell us the singular point and the nature of that singular point. Now from here, we can divide both sides by the coefficient of the highest order. That is why I said that you divide both sides by 9x1 minus x. So if you do that, what we have there is this expression. In this case now, this is my p of x. P of x over q of x over p of x, and the other one. So now looking at this, when x is 0, you see that everything here will be 0, infinite. So that's a singular point. And by the time x is 1, that is another singular point. So for this particular problem now, we have two singular points. Now the next question now is this: what type of singular point? Is it regular or irregular? So let's take a look at this. X p of x and x squared q of x. What I'm trying to say now is this. Look at this very well. By the time you put x here, you multiply this one by x. X will cancel x. So by the time you put 0, which is, if you want to check x equals to 0 now, you put 0 here, then you now see that what you have here is what? 12 over what? 9, and which is finite. And if that is finite, it means that it is analytic. And if it is analytic and this one is also analytic, it means that this is actually, we are talking about regular singular points. So because of that, we can proceed and use our method of Frobenius. Now, this is the series we are assuming now, equation 6. So let's differentiate the first time. K plus RL will come here, then minus 1. Then you differentiate the second time again. This is my differentiate equation 6, and this one differentiate equation 7. So look at it now. So now, next thing now is that for us to expand this equation, let's expand this equation 5. When you expand it, you obtain this. So let's substitute all the derivative back. So look at it now. This is y prime prime. This is what? Y prime. And this is what? Y prime. And this is what? Y. So look at it now. Then let's multiply it. Look at it. This is x, right? 1 will come and affect this one to give us minus 1. That is how we have minus 1 here now. Can you see that? And this one again, x squared will come in. 2 plus 2 minus 2 will give us 0. So that is why we obtain this. Now look at this one again. So minus 1, this one is just as it is now. So what is the next thing now? Next stage is for us to group the terms. So we are going to group this one and this one together because they have the same power, the same coefficient, which is r0 to infinity rsk plus r minus 1. Then let's group the second one again. We're going to group this one and then the last term. So we are grouping first and third, second and fourth to give us equation 9. So let's focus on equation 9 now. What is the next thing now? We need to obtain our indicial equation. We are setting r equals to 0 in everywhere in equation 9. So by the time you set r equals to 0 in everywhere, then which one is the lowest power? You see that by the time you put 0 here, this one will give me k minus 1. By the time you put 0 here, this one will give me honorary k. Definitely, x k raised to power minus 1 is lower than x raised to power what? K. So we are picking this one here. So we set the coefficient of this one equals to 0. So look at it now. Now look at the way I put it in my lecture. And I said, here comes the question. What is the question? Which of the power of x is the lowest? Equate its coefficient to 0. Hence, so this now we set this one equals to 0. Everything here. I mean this coefficient here. So we have the one equals 0, including a naught. In this case, remember that a naught is not 0, but others equals to 0. So if you expand this one will give you 9k squared. This and this give you minus 9k, and this one give minus 12k. That's how we obtain this expression. So minus 9k minus 12k give minus 21k. So we can actually factorize on 2 or 3k into bracket 3k minus 7. So from here we can see now that k1 is 0 and k2 is what? 7 over 3. That is the solution of our indicial equation. And from this particular, the next thing I want to call your attention to is this. If we look at the difference. What is the difference between K1 minus K2? You see that is the difference is actually 7/3 or minus 7/3, and which makes this problem to be of the first category. Look at the first category I explained earlier on. The first category, where is it? Okay, tutorial question. To look at the first category, I said K1 is not equal to K2. It's 0 and 7/3, they are not equal, right? And the difference is not an integer. So if the difference is not an integer, then we are going for this first category. So let's proceed now. So we have this. Now, what is the next thing now? See, please take a look at this. During the class, I actually did something I didn't explain very well. But recently, I come up with another way again to really come up with it. Now, let's take a look at this now. Let's focus on this equation 9. We want the power here to be equal to this power. Can you see that? Look at the way I put it in this lecture. I said, in equation 9, we want both power of x to be equal. Look at it, sk plus r minus 1 equals to sk plus r. The only thing I can do is that by the time I set my r equals to 1 in the first summation, I will set my r equals to 0 in the second summation. At the end of the day, you see now that both of them, they will now have x raised to power k. Now, let's look at equation 9. This is equation 9. In this summation, which is blue color, I'm going to set r equals to 1 in every way. Wherever I see r, put it 1. In this second summation, wherever you see r, you put a 0 there. Now, let's take a look at that. 9k plus 1. Look at it. K plus 1. Then plus 1 minus 1 will give you k. K plus 1 minus 1 will give you k. Then this one minus 12. K plus 1. Then summation 2. In this case, now r is now equal to what? 1. Let me change it. Thank you very much. My r is what? Is 1. Are we together now? Okay. But do you even notice that even either I change it or not, the summation will still vanish? Yes, it still vanish. Because I'm no longer using the old series. Do you notice? Note the series is from 0 to infinity. And we are not looking at that. What we are looking for now is that we are trying to consider the partition of that series. So this one will give me a1, r is 1, right? And then by the time you put 1 here, 1 minus 1 will give you 0. Now let's come to the second summation. In this second summation, we take r to be 0. So we have this one with k. This one is what is 0. That will give me k minus 1, then minus 1. Then this one will a raised to power a is not, then it's 0. Now look at it now. We have sk, we have sk. Are we together now? So we can throw them away because the summation, by the time you factorize the summation, are you getting that here? We equate that one to be what? The summation is not 0 anyway, but what is inside is what we are looking for. So we have all of them multiplied by x to the power k. What is the coefficient of sk? We check it equates what to 0. So we equate the coefficient, everything like this. We equate them to 0. So that's what we have here now. What is the next thing now? The next thing now is this. I will expand. If you expand this, you have this. If you expand this, you have this. Are you getting now? So that's not all. You take everything here. You take it to the other side. Because before it happens to be minus, then now it's now plus. So now another thing you now notice is this. The coefficient of a1 here is still the same thing as, look at it, 9k squared minus 9k minus 4 is the same thing as this minus 9. This minus 9, let me underline it. This minus 9, we can actually equate this minus 9 to be equals to plus 3k minus 12k. So from here, we factorize now, we have this one now. Also note this one again. We can also factorize this one too to give us 3 into bracket k plus 1, 3k minus 1. If you check very well, you can pause the video when you are studying. You see that they are equal. So from here, we can answer that a1 is equal to this. That's our equation 10. Now, look at what I've done here. Let me explain over again. What I've just done, what I'm trying to do here is this. From equation 9, I want the power of this one to be equal to the power of this one. What do I need? In this term here, I set my r equals to 1. In this term here, I set my r equals to 0. So the summation will vanish. Then I have a1, I have a naught. Then from here, I can get the first expression. Now let's now take a look at the reoccurrence. How do you now get the reoccurrence? Do I remember the method I explained to you in the class? So let me take a look. Look at equation 9 again. I'm back to equation 9 now. Okay. In this equation 9 now, I want the power of this one to be equal to the power of this one. So what do? I put star at the bottom of this my array. Because it's the lead term. It's one that will give me the lowest coefficient. So from here, I can see that my r side is equal to what? R plus 1. But minus 1 here, we go to the other side. So we substitute everything here into this first summation. In the second summation, we will only substitute it in this. I mean, in summation here without AR. Are we together? Like I've explained to you in the class, inside only this one. So now let's take a look at this now. Look at what I put. I said we shall substitute this into the first term only and the summation of the second term. So look at this now. Let me reduce the screen size so that we can see clearly, all of us. Now look at what we're having here now. Look at this now. This is 9k. R here will become what? R plus 1. R here will become what? R plus 1, then minus 1. 12 into k. Then this R will become what? R plus 1. Then this R here will become what? R plus 1. And then summation 2 from 1. So this one too, k is what? R plus 1, then minus 1. That is what we can see here now. So let's look at this one again. Look at this one. Minus 9k plus R. K plus R minus 1, then minus 4. Can you see that now? Can you see that? It is only the summation. Don't forget, it's only the summation here. Then you leave the others. So you see that now. So what is the next thing now? You factorize. Look at it now. You know, here the power. The power here we give you s raised to power k plus r. What about the power here? It's still the same thing because we didn't add anything. It's only the summation here. So what is the next thing? I said we factorize this. By the time you factorize, we have the coefficient of this one. Are we together? And the coefficient of the other one here, which is this. Then summation of, can you see that summation will come out as 1 to 1, 1 to infinity sk plus r equals 0. So what is the next thing now? We equate the coefficient equals what to 0. By the time you equate 0 to 0, then you have ar plus 1. Then this is our equation 11. So this is not the recurrence formula. So we now go back in case A of equation 11. That is case A. That is when k1 is equals to k is equals to 0. So wherever you see k here, you put 0 here. Then you now start over again. When r is 0, here I intentionally want to start again from r equals to 0 to see if this my recurrence formula here will give me the same thing with my equation 10. That is exactly the reason why I'm starting from r equals to what? 0. So I said when r is 0, I wish to start from r equals 0 in order to check if equation 10 is correct. If equation 10, if my recurrence formula will give me the same thing with equation 10, that's the exact reason why I'm trying to start all over again from r equals to 0. So when r equals to 0, so you put 0 here. You know, you have your a1 equals to 1 over 3 a naught. You do again. Now, let's look at check in equation 10. You set k equals to 0 again. You now see that both of them, they are the same thing. So what I'm not trying to tell you now is this. This method is very simple. But the only thing you need to do is this. By the time you have your normal, by the time you substitute everything, but you factorize, you have this equation. Set r equals 0 to get your indicia. From your indicia, you get your k. Now, the next thing is this. You go back again. You look for a way to set this power here to equals to this power. Then what do you do? Here, when r is 1, when r is 0 here. Are you together? So everything here, you said r equals to 1. Everything you said r equals 0. Then that is how you can get the first expression relating a1 to a naught. You know, there's some cases whereby we can just say that if this one will let us know the nature of a1. You know, there's some cases whereby we say a1 is 0. When we were solving Bessel differential equation of order n, do you notice that we impose certain things on this particular a1? In that case, we notice that our a1 is 0. Do you agree? Do you remember? Go and check your lecture notes. You see that when we are solving Bessel differential equation of order n, we said a1 is 0. So this one will help us to know, because from here, by the time you put those k here, you will know. If you return k into this expression, what I'm saying is that when k is 0, you put 0 here. When k is 1 over 7 over 3, you put it down here. That one will let us know if a1 should be 0 or a1 should not be 0. So that is it. So let's proceed now. So by the time you do that, you now see that from here that the recurrence formula we have and the expression we have relating a1 to a naught, they are, both of them are equal. So let's proceed. When r equals to 1, when r equals to 1 from here, from this particular expression, you return r equals to 1, then you get a2 as a function relating a1. You do the same thing again, you do the same thing, then you have the first solution. You go back again to the recurrence formula, you set k equals 7 over 3, then you do that one again, then you have this expression. It's very simple. I'm just setting when r is 0 into this expression in equation 12. So when r is 0, when r is 1, when r is 2, then I will obtain everything. Look at what I'm trying to do. You are not to leave the answer in form of a2. You are to put exactly, you are to put a naught. You have to make it as a function of a naught. So this is the series solution we are using. then you return everything back. Then you now say that the two linear independent solution is what? AY1 plus what? Plus BY2. So I believe you by now you're supposed to understand this method of Frobenius series integration. So don't forget, it's very simple, but I think the only place is this technical aspect. That is when you want to get the relation of A1 relating A0. I didn't explain this one very well during the class. Please pardon me for that. So that is why I'm releasing this video again, to explain this aspect. It's very simple. After you have this expression, which is you substitute everything, you expand, you want to set this one and this one to the same. So here you set your R equals to 1, you set your R equals to 0 here. Then by the time you do that, but if you want to get that of reoccurrence, by the time you set the power to the same thing, just like I've done here, you only need to substitute this thing in the first summation. In the second summation, you don't do anything except this part, except this side. That one is for the reoccurrence. So you can now check if the reoccurrence and the first one you obtained are the same. That is what I've just done here. So let's call it a day. Thank you very much. So wishing you all the best. Thank you. Bye bye.